In this video we're looking at displacement time graphs, and of course displacement is the vector version of distance. Now what we've got here is we've got a man here starting at point A, and he's going to walk in the direction of the vector A to B along the horizontal. So the direction of the vector is defined in this horizontal direction, in the direction A to B. Okay. Now, and the distance is, say, from A to B, let's say, it's 10 meters, and starting there at 0 meters. So I'm going to represent this on a graph. So, draw a graph like that. Now, displacement, it can be represented by the letter S, and it often is when we look at Subat equations. So that's distance S in meters, against time t in seconds. Isn't that very confusing? So S here stands for displacement, and S here is seconds. Okay, so here we go. So he starts off walking along from A to B. Let's say he walks along at a steady speed for 4 meters, and it takes him, say, 8 seconds. So here we go. So put 4 on there, and we'll put 8 just there. So there he goes. So there we go. It walks from A to there, to there. So after 4 meters, it's taken him 8 seconds. Now, and that's how we represent it. He's walked at a constant velocity, and the velocity is simply the gradient. And the gradient doesn't change, so the gradient is the velocity is the gradient, and that will give us 4 divided by 8, which gives us 0.5 meters per second. He's in fact going rather slowly. In fact, he then decides to stop for 2 seconds. So showing you stop for 2 seconds means that time will move on like that. So I'll move at 8 a bit. Time moves on, and after 10 seconds, increase this a bit, he hasn't moved at all. After 10 seconds, there you go, he's still at a displacement of 4 meters. So he's had a rest. So there you go. I shall draw him vertically, lying down, having a rest. He's quite a sloth-like runner. Very, very sensible. Okay, so he's had a rest again, and now he decides, oh, he's had enough of the rest. He's feeling a little bit homesick, and he wants to return. So he's now going to return to where he comes from. So in fact, he then returns from here back to his starting position. So, and he's going to go a bit faster because he's very homesick. And we're going to say that in another 2 seconds, that moves up to 12 seconds, he rushes back home again. He's back home again, and his displacement now is 0. So in fact, he hasn't effectively, although he has covered a distance, is what he feels he's covered a distance. In fact, he's covered a distance of 8 meters. In fact, his displacement is 0. It's back again, and during that part, he's going to get a negative gradient. So the velocity here, which is the gradient, is going to be negative because it's sloping that way, and that is going to be, this time is going to be 4 divided in 2 seconds, which equals 2 meters per second. Now, what he could do, he could, if he wanted to, if he's so excited to be home, he could miss home, and he could, let's move this out here, give us up this space, he could go to home, and then he can carry on going past home. So in fact, we could then extend this down, you see, from there, and we actually get negative displacement. So let's say he goes 4 meters past, he goes here, and that would in fact be minus 4 meters. Okay, this would be minus 4 meters, and that would take him, when he's going at the same velocity, the same gradient, that would be take him up to 14 seconds, so in another 2 seconds. So therefore his velocity here, that's equal, so that's positive 2 there. Here he's got a velocity of, no, what am I talking about? Yes. His velocity is here minus 2 meters per second, and his velocity is still equal to minus 2 meters per second. Okay, he's going in the opposite direction, and his displacement is equal to minus 4 meters. Okay, so in the world of displacement and of velocity, we have negative, and of course in the world of speed and time, we cannot. Now I'll quickly rub that out, and we'll look at some other cases. Now, the gradient of the displacement time graph is the velocity. Now, let's say we do here displacement in meters against time in seconds. If we have a curve like that, okay, you will find here it is accelerating. Accelerating meaning that the velocity is increasing. So we take a point here, call that P. To find the instantaneous velocity, we draw a tangent like that. Find the gradient, and the velocity at P is equals the gradient at P. It's going to be positive, and then up here we can do the same thing. So the velocity at Q equals the gradient at Q. So we draw another of our triangles, and of course the gradient is equal to the change, which is a triangle, a change in y divided by the change in x. So that will be the y direction divided by the x direction. So we find that the velocity at Q is greater than the velocity at P, and as it's in time, because acceleration is equal to the rate of change of velocity with respect to time, or in calculus dv/dt, which you may or may not come across yet, and we find it with the velocity increasing, so therefore it is accelerating. Equally, well, not equally, but similarly, you find that if the graph, I'll throw my pen away here, if the graph is like this, displacement in meters against time in seconds, if it's going like that, it is of course decelerating. The velocity, the gradient, is decreasing. Okay.